In Dr. Michio Kaku's way of framing the cosmos, the universe is not a silent painting. It is a machine made of laws, and those laws can sing. Not in sound that air carries, but in vibrations of space-time itself, a hidden music so deep that a single note can take years to complete. The night sky looks still only because human senses are tuned to light and motion at human scale. A theorist trained in Einstein's geometry sees something else. Space and time are not just where events happen. They are part of the event. They can stretch, squeeze, and ripple as if reality has an elastic backbone. Somewhere far beyond the reach of any telescope image, enormous masses orbit in darkness, and their motion writes a faint signature into space-time. Two black holes circle, slowly tightening their dance, and the universe cannot keep that dance completely private. Geometry must respond. Ripples spread outward, not as light, not as particles, but as distortion in distance itself. Most of those ripples are too gentle to notice when they arrive here, diluted across billions of light years. But the universe is old, and it repeats its largest motions again and again. Over cosmic time, countless distant events overlap, layering their ripples into something that is not one dramatic burst, but a background, a deep gravitational hum threaded through the cosmos. This is where the Michio-style view becomes almost cinematic without needing spectacle. The universe behaves like a grand orchestra. Galaxies are not only islands of light, they are arrangements of mass. Black holes are not only monsters, they are instruments, and gravity is the conductor, enforcing rhythm with absolute discipline. The hum is not a message meant for anyone. It is simply what remains when the universe does what it naturally does at scale: merge, orbit, collide, and settle. In string theory language, the picture becomes even stranger. Reality is not merely objects moving through space. Reality is vibrations in a deeper structure. A particle is not a tiny bead. It is a mode, a note. And if the universe truly has extra dimensions folded tightly beyond perception, then space-time is not the whole stage, but only the part of the stage human senses can access. In that broader view, a gravitational wave background is not just an astrophysical curiosity. It is a hint that the fabric of reality has texture, that the universe carries an underlying rhythm that might be connected to the deepest framework beneath matter itself. The calm part is this: a universe that can sustain a faint hum for billions of years is a universe that is stable. It is lawful. It is consistent enough to be read. The same discipline that prevents easy shortcuts across the stars also makes subtle truth possible. The cosmos does not shout. It whispers in patterns, and it rewards patience with clarity. And if that hum is real, it means something quietly profound. Even in the darkest regions where no light is shining toward Earth, the universe is still leaving traces. The night is not empty. It is filled with structure too faint to see, but not too faint to measure. Space-time may be vibrating right now, carrying the memory of ancient motions, while a small planet continues to orbit an ordinary star, inside an ordinary galaxy, inside a vast web of galaxies, all floating in a reality that is far more musical than it looks. In Dr. Kaku's style of thinking, the universe is not only a picture, it is a set of rhythms. And when the rhythm is too deep for the eye, physics looks for something more reliable than vision: timing. The most powerful detector for an ultra-slow cosmic hum is not a camera. It is a clock. Not a clock made by hands and gears, but a clock made by gravity compressing a star into a point of almost unimaginable density. When a massive star dies, its core can collapse so violently that matter is crushed beyond anything found on Earth. Electrons and protons are forced into a new arrangement, forming a neutron star, an object with the mass of the Sun packed into a sphere the size of a city. It is one of the universe's cleanest demonstrations of how far physics can be pushed while still remaining stable. And some neutron stars become pulsars. They rotate rapidly, their magnetic fields funnel radiation into narrow beams, and as they spin, those beams sweep across the galaxy like lighthouse lights. To an observer far away, the pulses arrive with a steady beat, on and off, sometimes so regular that they can rival atomic clocks over long stretches of time. That regularity matters because a gravitational wave does not need to break anything to reveal itself. It only needs to change distance by a tiny amount. A passing ripple in spacetime stretches the space between Earth and a pulsar slightly, then squeezes it slightly. And that means the travel time of the pulses shifts. The pulse that should arrive at one moment arrives a fraction early or a fraction late. The effect is incredibly small, but it is not nothing. It is the universe leaving fingerprints in the one place it cannot hide from measurement: time. A single pulsar is not enough because the universe is noisy. Interstellar gas and plasma can smear signals. A pulsar can have tiny irregularities in its spin. Instruments have limits and models have blind spots. So the method becomes what a theoretical physicist would admire. It becomes statistical, geometric, and stubbornly patient. Many pulsars scattered across the sky are monitored together, forming a Pulsar Timing Array, a galaxy-scale network of clocks. The search is not for a single dramatic spike, but for a shared pattern across the whole network. If a gravitational wave background is washing through our region of spacetime, it should imprint a correlation in timing shifts that depends on where each pulsar sits in the sky, like a slow swell passing through an ocean, lifting different points differently while still belonging to one underlying motion. In this approach, the Milky Way becomes part of the instrument. The galaxy supplies the clocks, Earth supplies the patience, and the universe supplies the signal if the signal is there. Over years, sometimes decades, the pattern can sharpen, separating itself from noise the way a faint melody becomes recognizable only after it repeats enough times. This is the quiet genius of it. The method does not demand that the cosmos shout. It assumes the cosmos whispers, and it builds a way to listen anyway. And there is a deeper implication that fits the multiverse mindset without needing fantasy. If space-time can be measured at this level of delicacy, then the universe is not only vast, it is coherent. It is consistent enough that the tiniest deviations can be tray. If a pulsar timing array is a way of listening, then the next step is to ask what the universe is actually playing. In Dr. Kaku's perspective, the most interesting questions are never, is it possible, but what does the structure of reality allow? A deep gravitational wave background, if it is there, is not a single event. It is the combined aftertaste of countless events spread across the cosmic web. And that immediately narrows the suspects to things that are both common and massive, or things that are rare but fundamental enough to leave a persistent imprint. One suspect is almost inevitable in a universe built from galaxies. Most large galaxies appear to host supermassive black holes in their cores, not stellar-sized, but millions or billions of solar masses. Over cosmic time, galaxies collide and merge. The stars usually pass by each other because space inside a galaxy is mostly emptiness, but gravity reorganizes everything anyway. As two galaxies blend, their central black holes can become bound into a slow binary system, orbiting in the dark like two heavy dancers on an invisible stage. The orbit shrinks gradually, sometimes helped by surrounding stars and gas that steal away orbital energy, and eventually gravity itself becomes the main way energy leaves the system. That escape route is gravitational radiation. Because the masses are gigantic and the orbital periods are long, the waves are not high-frequency bursts. They are deep, ultra-low-frequency ripples, the kind that fit naturally into the timescales that pulsars can detect. Now stretch that picture across the observable universe. Not one pair, but an uncountable number of pairs at different distances and different stages of their inspiral, each contributing a low note. The notes overlap. They blur together. The result is not a clean melody, but a background, a gravitational choir made from the slow evolution of structure itself. This explanation has a brutal simplicity that theoretical physicists respect. It requires no exotic new substance, only the universe doing what it already does naturally, building galaxies, merging galaxies, growing black holes, and letting gravity carry away energy. But there is another suspect that belongs to a deeper layer of the story, the layer where Dr. Kaku's favorite themes often live: the early universe, symmetry breaking, and the possibility that what we see as particles are really vibrations of something more fundamental. Cosmic strings, if they exist, would not be strings of ordinary matter. They would be defects in the configuration of fundamental fields, like seams left behind after a rapid transition when the universe cooled and settled into its present laws. The analogy is not perfect, but it is useful. When a substance undergoes a phase change, it can trap imperfections, boundaries, or stress lines. If the early cosmos underwent transitions as forces and fields rearranged themselves, it could have left behind relic defects that are stable for deep mathematical reasons. A cosmic string would be one of those relics, extraordinarily thin, yet carrying immense energy per unit length, enough to curve space-time around it, even though it occupies almost no volume. Cosmic strings become relevant to this hum because they would not simply sit there. They could move, vibrate, intersect, and form loops. A loop of string would oscillate like a stretched band under tension, and as it oscillates, it would lose energy. One of the cleanest channels for that energy loss is gravitational waves. Over cosmic time, countless loops could form and decay, each sending out ripples into space-time. Layer enough of those ripples together across the universe, and once again, a background appears, but with a very different origin. The black hole choir would be the sound of a mature universe, galaxies and mergers, and slow gravitational dances. A cosmic string background would be the echo of a younger universe, a relic vibration tied to the earliest conditions, possibly connected to the deeper frameworks that try to unify quantum mechanics with gravity. This is where the multiverse flavor can enter without turning into fantasy. In many early universe scenarios, the vacuum state is not necessarily unique. Fields can settle into different configurations, and the universe can, in principle, explore a landscape of possibilities. In some models, inflation does not end everywhere the same way at the same time. Regions can become causally isolated. Outcomes can differ beyond any horizon. Cosmic strings, in that context, are not just objects. They are the kind of scars that can form when a universe chooses one local arrangement of fields, while other arrangements may exist elsewhere, forever out of reach. No one needs to claim this is true. The point is that a gravitational wave background could become a test, a way to push these big ideas out of pure mathematics and into the realm of fingerprints and data. How would the universe reveal which suspect is responsible? Not through a dramatic announcement, but through the shape of the signal. Different sources tend to produce different spectral patterns, different distributions of power across frequency, different statistical behaviors as measurements improve. A background dominated by supermassive black hole binaries carries the imprint of galaxy merger rates and black hole populations. A background with a significant cosmic string contribution could show a different slope or additional features that do not fit the simplest astrophysical expectations. The work is slow because the signal is faint and the data must be collected over long spans. But that slowness is not a flaw. It is the cosmos speaking in its native tempo. If you are enjoying this kind of quiet, physics-forward storytelling, support the channel by liking the video and subscribing. It tells the algorithm that calm science belongs in people's nights, and it helps this series keep going. In the end, the hum, if it becomes undeniable, will not only be a detection, it will be a choice point. Either the universe is humming mainly because galaxies are constantly reshaping themselves through black hole mergers, or it is humming partly because the early universe left behind relic seams that still ring today. Either outcome is extraordinary. One would be a census of cosmic evolution written in gravity. The other would be a clue that the deepest structure beneath matter and forces has left an audible trace in space-time itself. The signal, if it is real, does not arrive as a single clean note. It arrives as a pattern that has to be earned. A theoretical physicist would expect that, because the universe rarely hands out answers in one piece. It hands out constraints. It hands out correlations. It hands out shapes that become sharper the longer they are stared at with discipline. With pulsar timing arrays, the most important evidence is not that one pulsar seems early or late on a given day. The important evidence is that many pulsars scattered across the sky begin to drift in a coordinated way that matches the geometry of a gravitational wave background. The delays are tiny, but the relationship between them is not arbitrary. It depends on angles across the sky because spacetime is being distorted in a way that has a global imprint. If that angular correlation strengthens with time and survives every sanity check, then the hum stops being a poetic idea and becomes a physical feature of the universe. But even after the background becomes convincing, the deeper question remains: what is it made of? In the Michio-style worldview, this is the moment where the universe becomes a courtroom. Two suspects stand under the same light, and the verdict depends on fingerprints, not on desire. The first suspect, supermassive black hole binaries, is almost unavoidable. Galaxies merge, black holes pair, gravity radiates. The second suspect, cosmic strings, is more exotic but more fundamental. A relic possibility from early universe transitions that could leave a persistent gravitational signature. Both can produce a background. Both can live in the low-frequency range. So the only way forward is to ask what each suspect would naturally leave behind in the data. A background from supermassive black hole binaries tends to be shaped by astrophysical history. How often do galaxies merge? How massive are the black holes? How quickly do binaries evolve? How much do surrounding stars and gas help or hinder the final in-spiral? The answers sculpt the spectrum, the way the signal strength changes with frequency. In many realistic scenarios, the background has a characteristic reddish nature, meaning more power at the lowest frequencies because the slowest, widest orbits dominate the long timescale ripples. The signal may also carry hints of anisotropy, not perfectly uniform across the sky, because matter in the universe is not perfectly uniform. The cosmic web is lumpy. Structure clusters. If enough nearby or particularly massive systems dominate, the background could be slightly brighter in certain directions. Cosmic strings, in contrast, can leave a background with different habits. String loops form and decay across cosmic time, and depending on the string tension and the loop distribution, the spectrum can have a different slope, sometimes extending in a way that is less tied to galaxy demographics and more tied to early universe physics. Strings can also produce burst-like features, sharp emissions from kinks or cusps on oscillating loops, which could make the background less perfectly smooth in a statistical sense. A theorist would describe this as a difference between a signal that is mostly Gaussian and blended versus a signal that might have more rare, sharp contributions embedded in the overall hum. This is not guaranteed. It depends on parameters, but it offers a route. The background is not only present or absent, it has texture. This is why the next phase of listening becomes more demanding. It is no longer just detection. It is diagnosis. The network must grow. The timing must extend over longer baselines. Systematics must be crushed. The interstellar medium must be modeled with more precision because plasma effects can imitate low-frequency timing noise if handled carelessly. Individual pulsars must be understood well enough that their own quirks do not masquerade as cosmic geometry. A theoretical physicist tends to love this stage because it is where the romance of big ideas is forced to survive the cold discipline of data. The universe does not care what anyone hopes is true. It only cares what its equations and initial conditions actually produced. And there is a larger frame around all of this that fits naturally with multiverse-flavored thinking. The deepest limitation is not technology. It is causality. Even the most advanced civilization cannot transmit usable information faster than light in normal space-time, and it cannot step outside the light cone structure without breaking the consistency that makes physics possible. That causal architecture is precisely why gravitational waves matter so much. They obey the same limit, they travel at light speed, they respect the same structure, they do not cheat, they reveal, they carry information not by violating the rules, but by using the rules in their purest form. In that sense, hearing a gravitational wave background is hearing the universe's causal skeleton. It is a measurement of the framework that all possible civilizations must live inside, whether they build radios, lasers, or something far beyond human imagination. There is also a quiet irony here. The universe may be full of intelligent life and still be unreachable in the social sense, because distances and horizons are real, but the universe can still be reachable in a deeper sense, because the laws are universal. A civilization does not need to meet another civilization to share the same physics. The same geometry that governs black holes near the center of a distant galaxy governs the timing of pulses from a dead star in the Milky Way. The same field equations that allow cosmic strings as a possibility, if they exist, also govern gravity on a planet with oceans and forests. A theorist would call this the most profound form of connection available. Not conversation, but coherence. Not contact, but shared law. So the listening continues with a very specific goal, not just to confirm that spacetime hums, but to learn what kind of universe produces that hum. A universe where the dominant source is the slow choreography of supermassive black holes assembling structure over billions of years. Or a universe where part of the hum is older, tied to early transitions, hinting at deeper layers of reality beneath the particles and forces that are seen. Either way, the night remains calm. The signal is not a threat. It is a clue. It is the universe allowing itself to be read, one tiny delay at a time. Once the hum begins to look real, the universe becomes more than scenery. It becomes a system that can be interrogated in two languages at once, light and gravity. Light tells you what shines. Gravity tells you what moves, and in the deepest sense, what reality is willing to allow. In the Michio-style view, that is the seductive part of physics. The cosmos is not only vast, it is structured, it is lawful, it can be modeled. And sometimes, if the instruments are sensitive enough, the laws reveal themselves in places where no image could ever form. A gravitational wave background is one of those revelations. It is not a single collision. It is the collective imprint of countless motions that the universe cannot hide. In practice, it becomes a new kind of survey. If supermassive black hole binaries dominate, the background becomes a statistical map of how galaxies grow and merge across cosmic history. It tells a story about the universe building itself, the rate of mergers, the distribution of black hole masses, the way matter and gravity sculpt the cosmic web. It is not just noise. It is a record encoded in the only channel that can pass through everything without being blocked. Geometry. If cosmic strings contribute, the meaning shifts in a sharper, more foundational direction. Strings are not just another astrophysical population. They are a statement about early universe physics. They would imply that when the universe cooled and its symmetries broke, it left behind topological relics that survived, not because they are strong in the usual sense, but because they are stable in a mathematical sense. If those relics still ring, then the background is not only the sound of galaxies. It is a fossil vibration from the universe's earliest transitions. It becomes evidence that deep field dynamics left scars in reality's fabric, scars that can still be detected today by measuring time carefully enough. And this is where the multiverse theme can enter in a way that remains disciplined. Many of the theories that produce cosmic strings also live in a landscape of possible vacua, where fields can settle into different configurations. Inflationary scenarios can produce horizons and isolated regions, and in some models, different domains can realize different outcomes. Cosmic strings, in that context, become more than objects. They become hints that reality's choice was not necessarily unique everywhere, that the early universe may have had multiple ways to settle, leaving defects as boundaries and relics. This does not prove a multiverse. It does not automatically open doors to other universes. But it does something just as important in science. It narrows the space of possible stories about the beginning. It turns metaphysical-sounding ideas into testable fingerprints. The fingerprints matter because theoretical physics is not a philosophy club. It is a tool for making predictions that survive contact with data. If the background spectrum matches what is expected from supermassive black hole binaries, then the universe is confirming a picture of structure formation with gravity as the main architect. If the spectrum refuses to fit, if it shows features more naturally explained by a cosmic string network, then early universe physics becomes less abstract and more concrete. Either way, something profound happens. The universe is not merely being observed, it is being constrained. And in physics, constraint is the path toward truth. There is also an implication that sounds almost personal in a quiet midnight setting. Even if no civilization ever meets another civilization across the stars, the universe still provides a kind of connection through law. The same mathematical framework that governs black holes in distant galaxies governs the timing of pulses in our own. The same causality that limits travel also preserves coherence. The speed of light, the structure of light cones, the conservation of information within those boundaries, these are not inconveniences. They are the architecture that makes the universe stable enough for clocks to exist and for clocks to reveal deep structure. A theorist would also point out the elegance of the method itself. The instruments are not gigantic machines in space the size of cities. They are clocks scattered through the galaxy, and the human role is to listen long enough to find a pattern. This is not brute force. It is patience turned into precision. It is the scientific method in its purest form. Take a subtle prediction from theory, build a way to test it, then wait long enough for the universe to answer in its own tempo. If the answer becomes clear, it changes what discovery looks like. A discovery is not always a photograph. Sometimes it is a curve on a plot, a slope in a spectrum, a correlation across the sky that refuses to vanish. Sometimes it is the realization that space-time itself has a background vibration, and that this vibration carries information about the largest structures in the universe, and possibly about the earliest conditions that shaped everything that came after. In that sense, the hum is not merely an object of curiosity. It is a bridge between the very large and the very early, between galaxies and the newborn universe, between what is seen and what is only felt through time. And quietly, beneath all the complexity, a simple truth remains. The universe is patient. It does not rush answers, but it does not hide them forever either. If a background hum exists, it will continue to wash through space-time, indifferent to whether anyone notices. The only question is whether the listening becomes sensitive enough, and steady enough, and long enough, for that faint cosmic baseline to be recognized as real. In the end, the hum, if it is truly there, does not make the universe louder. It makes the universe deeper. It reveals that the night sky is not only a field of light, but a field of geometry, a quiet structure that can carry motion for billions of years without losing its coherence. In the Mikio-style view, that coherence is one of the most comforting facts science has ever uncovered. Reality is not random. It is lawful enough to be read. It is stable enough to preserve faint signatures. And it is consistent enough that a small civilization on a small planet can measure the universe's most delicate movements using nothing more than patience, mathematics, and time. A gravitational wave background is not the kind of discovery that arrives with fireworks. It arrives like a slow realization. A pattern strengthens. Correlations persist. Alternatives fail. The signal does not shout. It simply refuses to go away. And once it becomes undeniable, it becomes a new way of knowing. The universe can be studied not only through the light it emits, but through the way its mass bends and vibrates the fabric beneath that light. That is a second sense, a second channel of truth, and it makes the cosmos feel less like an empty stage and more like an active instrument. If the background is dominated by supermassive black hole binaries, then the universe is confirming that gravity is always working in the dark, assembling, merging, reshaping structure across cosmic time. The hum becomes a census of hidden dances at galactic centers, a record of mergers too distant and too slow to watch directly. If cosmic strings contribute, then the meaning becomes even more fundamental. The universe may be carrying relic seams from its earliest phase transitions, still vibrating today. That would not prove every grand idea attached to it, but it would signal that the early universe left behind measurable structure in space-time itself, and that modern instruments have become sensitive enough to touch the beginning without ever leaving the present. And that brings the multiverse theme to its most disciplined form. The multiverse in serious physics is not a fantasy of portals. It is a consequence that can appear when fields have multiple stable states, when inflation and horizons split regions apart, when the early universe explores a landscape of outcomes. If the universe contains relic defects like cosmic strings, it strengthens the case that early universe physics is rich, layered, and not fully captured by the simplest pictures. It would suggest that reality has more architecture than what is visible in starlight alone. But even then, the message remains grounded. What matters is not what sounds exciting. What matters is what leaves fingerprints. There is also a calmer interpretation that works no matter which suspect wins. Even without contact with other civilizations, even without dramatic signs in the sky, the universe is still speaking through its laws. The same equations that describe electrons also describe galaxies. The same geometry that guides a beam of light from a pulsar also carries a ripple from a pair of black holes billions of light years away. That universality is a kind of connection that does not require meeting. It is coherence across distance. It is a shared framework that would apply to any intelligence anywhere, whether it lives under a red dwarf, inside an ocean beneath ice, or in a world that has never seen a star the way Earth does. So the night can be allowed to feel less like a void and more like a quiet library. Light is the ink, gravity is the binding, space-time is the paper. Every orbit, every merger, every early transition writes something into that library, and a patient civilization can learn to read it. The darkness is not an enemy. It is the space that keeps the pages from being burned by constant chaos. It is what makes long-term patterns possible. It is what makes the hum detectable at all. If you've made it this far and this helped you slow down, take a second to like the video and subscribe. It keeps this Calm Science series alive, and it helps more people find a quiet place to rest their mind while the universe keeps unfolding. And now let the final thought settle gently. You are on a small planet inside a thin atmosphere, breathing warm air while most of the universe remains cold and silent. Above, stars shine with ancient light. Beyond them, galaxies drift and merge. And beneath everything visible, space-time may be vibrating with a low, persistent note that carries the memory of ancient motion. The night is wide. The distances are real. The cosmos is patient. And in the middle of all that vast quiet, you are here, safe, breathing slowly, while the universe continues its gentle unfolding around you. Good night, and sleep well.